Today's lesson is looking at your final strategy for numerical methods for solving equations, not for integration. And this numerical method is called Newton Raphson, and you'll find it in chapter 14, section 2 in the textbook. For your starter, you're going to be presented with 8 different graphs, and for every graph, I want you to think about, is the graph going to be a cobweb or staircase diagram? Is it going to converge to a root? If there's more than one root, which root? Okay, and then you check it by drawing on the graph and calculating using the recursive menu on your calculator, or you could use the run mode and exe. Okay, and then once you've got your answers, you can decide why were you right or wrong. Okay, why is it a cobweb? Why is it a staircase? Why does it go to that route? And finally, use the correct terminology to describe the convergence or divergence. Okay. Here are your first 4 questions. They look a bit fuzzy. They're clearer on the PDF, so you can print that out and draw on it. Here's the last 4. Here are the solutions, and the last 4 solutions. Okay, this is the second example, or the second question there. So why did every single one of those 8 questions converge? Okay. And can you think of how you would sketch a diverging example? Well, if you remember, let's look at the curve here. It's pretty flat at the solution that it converges to, but pretty steep at the one it doesn't. So in order to converge, the gradient has to be between -1 and 1. And if you wanted to sketch a diverging example, you'd simply need to have a steep gradient. And what equation does the iteration solve? Well, let's look at our iteration formula, and if you just wrote the formula without the subscript n or n+1, you'd end up with the equation that you solve, which is of the form x is equal to f of x. How was this sensible starting value chosen? Okay, it was just given to us, but if you have to choose it, you could sketch the graph, or you could use a sign change rule. But with the sign change rule, you have to make sure you have rearranged your equation to make it equal 0 first. The question 7 had a really slow convergence, which is very tedious. So we're going to be looking at a much more efficient method. The Newton Raphson method is much quicker, and it's the one that your calculator uses when using solve n. So Newton came up with this process. I think it'd been known for a lot longer, but he came up with a nice formula for polynomials, and then Raphson extended it to be more general in 1690, so it's pretty old. Okay, let's remind ourselves, what do we mean by a root of a function? So the root of an equation is a solution of an equation. The root of a function is where the function is equal to 0. So what's the x value when the function equals 0? Or what's the x value when the graph cuts the x-axis? So for our formulas before, they were not equal to 0, so you just have to rearrange it to make it equal 0 first. Unfortunately, even if we have a function equal to 0, we can't always get something satisfactory. So even if we can find a formula that works, sometimes the exact solution is so hideous it's not worth writing down, and we prefer a decimal. And in other situations, so here we've got x is equal to cos x, so x minus cos x is 0. That hasn't got an algebraic expression to solve it. We can't find an exact solution. In that case, we can use a numerical method. So you've learnt the one where you rearrange the equation to get x equals something, and then you can use an iterative process based on that to get a solution with the cobweb and staircase diagram. Instead, we're going to keep the function equal to 0 and look at a method that works in that situation. So here's the Newton Raphson process. We can see we have a root at alpha, so that's where y equals f of x is equal to 0. Here's our first guess, x0. It's not very close. But if we look at the graph, okay, and find where our function is for our guess, then we can draw a tangent there, and if we follow the tangent down to the x-axis, we get a new guess that's definitely closer. And if we repeat this process, so here's our second guess, we draw a tangent to the curve at the point x1 and we get our next guess x2. That's a lot closer already. We could keep doing that to get as accurate a solution as we want. Okay, but we need a nice formula that's going to work. Let's work one out. So here's our first guess, xn. How do we find this second guess, xn plus 1? Well, we need to have the tangent to the curve of y equals f of x at xn, and then we need to see where that tangent crosses the x-axis. So we will need the equation of the tangent. And for the equation of any straight line, we need to have a gradient and a point. So the gradient is simply going to be the gradient of f of x at xn, and the point is where it touches the graph. So there's our equation of a line general formula from coordinate geometry in year 12. We're going to replace the x1 and y1 with the point, and we're going to replace the m with the gradient. Now we need to know, where does this straight line cut the x-axis? Okay, well, it cuts it at the point xn plus 1, 0. So we substitute in, instead of x we put xn plus 1, instead of y we put 0. And then we want to find out a little formula for xn plus 1. So we're going to make that the subject. First we're going to divide by the gradient, and then we're going to add xn plus 1. Happy times. So now we've got xn plus 1 on its own. So this is the Newton Raphson iterative formula. You will be delighted to know that this is on your formula sheet. Happy times. Have a look at this this animation. So there's our first guess, tangent, second guess. Tangent, where it cuts the x-axis, third guess. Tangent, where it cuts the x-axis, fourth guess. And here we're getting really close for that fifth guess. I think there's a pretty good animation there to see how that works. Let's go to an example, just a rough example. We're going to go for 3 decimal places here. So here's an equation, x equals cos x. We're going to have a starting value of 0.5. Okay, and so we need to rearrange this to make sure we've got f of x as 0. So we'll just subtract cos x from both sides. Now we look at our Newton Raphson formula, and we can see that we need to differentiate. So let's differentiate our function. When we differentiate negative cos, we get positive sine. And now we can just pop it into the iterative formula. Then we get the calculators out, and I would use the recursive menu. Okay, on the recursive menu you can type in your formula here, and then you press set. We're going to do the first 10 iterates, and our starting value A0 is 0.5. We don't need anything else because we can't, the cobweb and diagram's no use to us, so that A str thing is useless. Okay, I much prefer using this recursive menu to just doing it in run mode, although run mode is pretty quick, because you have a little table you can keep track of which iterate you're on and so on. Okay, so this gives us first iterate, second and third. Now notice that I have done lots of working out here. If it's a detailed reasoning question, or it says determine, I would need to write out my formula with my f of x in it. Okay, and then I would need to write out the formula substituting my first guess in and write out my answer. Then I'd write my next few guesses, and then if I need it to a high degree of accuracy, I'd just put ... and the last 2 guesses. But here, look at this. We're already, by the third iterate, we're agreeing to 3 decimal places. So that's pretty fast. Okay, we're going to break this into steps. So first of all, just practice writing the recurrence relation using, that's the iterative formula, using your Newton Raphson formula that you get given. Okay, here's your first answer. Here's the second one. Now you can just leave it as it is. Don't mess with it. Okay, don't mess with it. Just leave it unless the question says in the form such and such, or show that it equals to this. Okay, and here's the last one. Right, next we're going to try out one iterate. So here we've got our function, and we know that we want to find where the function is equal to 0, and that answer would be beta in the interval -2 to negative 1. If we take negative 1.5 as the first approximation, we just have to apply Newton Raphson once to get the second one. That's all we're asked for. So we need to work out what is our Newton Raphson formula. There's the original. We substitute in our function, differentiating for the second line, okay, the denominator. And then we just pop our negative 1.5 into that and see what we get. And then we round it to 2 decimal places. So you have a go at this one. Here are your answers. Here's a more general example. So we're given our function equal to 0. And so we want to find the positive root for that, correct to 6 decimal places. We are not given a starting value. So our first task is going to be try and find one. So we'll sketch it on the graph. Now on your calculator you might need to use zoom or view window to get where you can see the sensible roots, and you can just look at the graph, or you could use gsolve to help you find the sensible root. So here we are, we can see we have a negative and a positive root. This is the positive one. To me it looks pretty close to 1.2. So I'm going to use that as my starting value. And now we need to use Newton Raphson, and we're going to use the recur menu on the calculator. So there's Newton Raphson formula. Let's work out the formula. We've differentiated the x to the 6 minus x minus 1 for the denominator. And now we pop that into the recur menu. Okay, I'm going to have the first 10 iterates, and I'm going to start at 1.2, then press my table, and these are the numbers I end up with. And so I've got them to 7 decimal places here. We can see that the third and fourth iterates agree to 6 decimal places. Brilliant. Now, part B. We have to show that this is indeed correct to 6 decimal places. So all we do is we're going to use the sign change rule for values either side of the root to 6 decimal places, it should say. Okay, so this is substituting in half a unit to the left, okay, so smaller, and then we substitute in half a unit greater, and we can see that the first one is below 0 and the next one is above 0, and so by the sign change rule the root rounds to 1.134724 to 6 decimal places. Here are some questions for you to have go at from the textbook. Here are the quick answers, and I'm going to now show you the worked solutions from the textbook. Here's for the next page. And that's it for today. Well done. Bye for now.